The next operation, which is a derived operation, is known as the difference of sets. Okay, so we talk about A minus B or B minus A. So the set A minus B consists of all elements that are in A but not in B. So another way of saying it is that X belongs to A and X does not belong to B. Now I make an assertion here that difference operation is not commutative. That is, A minus B is not equal to B minus A in general. Can you give an example for this?
Okay, so A is say a set of 1 to 10, natural numbers, right. 1, and B is say from 6 to 10.
So tell me, what is A minus B in this
sir,
case?
So sir, in this case, A minus B would be 1 to 5. So not belonging to this set 1 to 5, and B minus A would be
null set or empty set.
Yes.
So here you see that A minus B is 1, 2, 3, 4, 5. All the elements of A which are not in B, which is 1, 2, 3, 4, 5. And B is all the elements of B which are not in A. And all elements of B are in A. So B minus A is equal to the null set. So therefore, A minus B is not equal to B minus A in general. In some special cases, it might happen, but in general, this will not. Okay. So if you get A minus B as null set, what can you say?
A is the subset of B in that case.
A is a subset of B in the. And what is B minus A is null?
B is the subset of A.
So if it happens that A minus B is null and B minus A is null, then what can we say?
Equal sets.
If A minus B is null, A is a subset of B. If B minus A is null, then B is a subset of A. Then we can conclude that A is equal to B. So there is another operation which is close to this. This is known as the symmetric difference of sets. This is again a derived operation. So it's denoted typically by delta. So A delta B is A minus B union B minus A. Look at this question. So can you now answer this question?
Yes, sir, it's equal. And the answer to that question is both are equal because...
So now in general, we can write A delta B as A union B minus A intersection B. So difference of these two sets, A union B minus A intersection B, that is A delta B. A delta B is equal to B delta A, so it is commutative. And A delta phi is equal to A. So let us...
X belongs to A delta B.
Okay. So let X belongs to A delta B.
That means that X belongs to A minus B union B minus A, which means that X belongs to A minus B or X belongs to B minus A. X belongs to A and X does not belong to B, or X belongs to B and X does not belong to A.
X belongs to B. If, since this is an OR statement, one of these has to be true. So if X does not belong to A, then X has to belong to B. If X does not belong to B, then X has to belong to A. So X has to belong to either A or B. That is, X belongs to A union B. And now what we are seeing? We are looking at the case where X belongs to both A and B. So X belongs to both A and B means X belongs to A, that is fine. And X does not belong to B part is false. So this is false. Similarly, X belongs to B is correct, but X does not belong to A is false. So both parts are false. So that cannot happen. Okay? So X belongs to A and B, that is ruled out. So X belongs to A union B, but X does not belong to A intersection B. So that gives us X belongs to A union B minus A intersection B. So what we have shown is A delta B is a subset of A union B minus A. So let's go the other way.
So suppose let X belong to A union B minus A intersection B. This means that X belongs to A union B but does not belong to A intersection B. Come to A minus B union B.
It says that X is in either in A or in B, and X is not in both of A and B.
Yes.
So that means if X belongs to A, can it belong to B?
No.
So, and X does not belong to B, or X belongs to B and X does not belong to B. That means X belongs to A minus B, or X belongs to A, which implies. So here we have shown that A union B minus A intersection B is a subset of. So combining one and two. So this is how typically these proofs are done in a formal